Hello, how you doing, Mindsetters? My name is Pumi, and it is, of course, a beautiful Thursday evening. I'm joined in studio today by Michelle, who's going to be doing geography for the grade 11s. How you doing, Michelle?
Fun and you, thanks, Pumi.
I'm good, thank you. Are you
Good.
feeling excited about today's show?
Yes, I am. I mean, it's a while since I've been able to go through the grade 11 syllabus again. I really enjoy the syllabus, and there's a couple of really nice questions that I've got for them today. So I'm hoping that they'll be tuned in. I told my own grade 11s that they should watch, so
Great
hopefully
stuff.
they'll be watching too.
Awesome stuff. Shout out to you guys right there at home. I'm hoping that you guys are ready and excited about tonight's show. Please remember that we are also running the K53 hashtag Be a Bright Spark competition. I'm sure that you guys at home are really hoping to win the Chevy Spark L, which is a very nice portable car. And if I had it my way, I'd really enter so that I could actually get to win. So guys, if you haven't entered, it is very simple. All what you have to do is just to buy the Safeways K53 book from your Samsung Galaxy application, or you could also go get it from Google Play Store. That is where you can download the application, and also you can actually get to buy the actual book from any retail store. Make sure that you keep the receipt as proof of a purchase. And then at number 2, make sure that you like us right there on our Facebook page. It is facebook.com/learn extra, and also facebook.com/Safeways K53. After liking those pages, you will actually get to click on the win a Chevy Spark L, and then that's where you're gonna get your application form so that you can enter. And straight after entering, make sure that you also share it so that your friends can also get to join. So after that, guys, you are automatically going to get yourself an extra entry. It is just as simple as that. It's very fun. I'm really hoping that you guys are going to be taking part in it, because it is closing on the 14th of November. On the 15th of November, which is next week, Friday. But without any further ado, grade 11s, I'm hoping that you are ready and excited. Please post all of the questions that you have on Facebook so that I can ask Michelle to try and help us in answering all of them. So yeah, Michelle, I'm ready. Aren't you ready?
Yes, I am. Thank you very
Awesome
much,
stuff.
Pumi. All right, grade 11s. We are going to be looking at a few select exam questions from the grade 11 syllabus today. We only have an hour, so I've chosen a few that I think that most grade 11s tend to struggle with a little bit. So there's a little bit of climate and weather in there. There's a little bit of geomorphology, one or two things about development and development aid as well. So we'll see how far we get through those questions in this lesson. Let's have a look, though, from the first part, the climate part. Okay, so we are working through exam questions from grade 11 syllabus relating to climate and weather, but as I said before, we're also going to be looking at development related questions as well as geomorphology. Right, question 1, we always get short questions that we start off with, and if we read the instructions carefully, it asks us to complete each of the following statements by choosing the correct word or term from the list below. And if we have a look there, a couple of options. We've got global air circulation, westerly winds, trade winds, those are also known as tropical easterlies, geostrophic wind, that's an interesting one we'll discuss in a second, Coriolis force, pressure gradient force as well. So let's just have a look at the simple questions we have and see if we can match each of those terms or the correct terms to each of those sentences. So 1.1 says the something causes air to be deflected from its original path. Now, when we taught this section, we said that wind usually would blow from a high pressure to a low pressure. The difference between a high and a low pressure being pressure gradient, and the force that acts on that air, causing it to move from an area of higher pressure to an area of lower pressure, which is called pressure gradient force. Now, we're assuming that air flows directly from high to low pressure. But when we think about the Earth spinning on its axis, air cannot flow directly from high to low pressure in a straight line. It gets deflected because of that spinning action of the Earth. And we should know by now that that action is called Coriolis force. So Coriolis force is causing that wind to be deflected from its original path. Now, in each hemisphere, it gets deflected in a particular direction. So in the northern hemisphere, if you're standing with your back to the wind, the deflection will be to the right. And if in the southern hemisphere, you're standing with your back to the wind, that deflection will be to the left. And we have a name for that. It's called Ferrell's law. So they ever ask you to describe Ferrell's law, it talks about the direction in which the wind is deflected due to the spinning action of the Earth on its axis, and that's called Coriolis force. So to cut a long story short, the answer that we're looking for is indeed Coriolis force. All right, and that will get you your 2 marks. Not so bad. Question 1.2. It says a large-scale movement of air, emphasis on the word large-scale, the phrase large-scale movement of air, in the atmosphere is referred to as what? Okay, if you have a look at our terms there, the correct option that you should be choosing is global air circulation. Now, in the old grade 12 syllabus, the first thing that I taught, well, I always teach my grade 12s, is that we basically get 3 levels of air circulation. When we're talking about global air circulation, it's on a very large scale, it's on a global scale, and we usually refer to that circulation as being permanent. It means the winds, the pressure belts, their characteristics don't change. We can also refer to that as primary circulation. So global air circulation and primary circulation mean the same thing when you're looking at the global tricellular model, for example. Now, just to let you guys know as well, we also get subcategories of circulation within that global air circulation. All right, so we've got our primary circulation. Now, within all of those are our pressure systems, our high pressures and low pressures, our global wind belts. We get something called secondary circulation. Now, secondary circulation is something that you guys are going to be introduced to very early on next year when we do tropical cyclones and mid-latitude cyclones. And those generally occur on a shorter time frame, a couple of weeks maybe, and they usually are not quite as large as our global air circulation. They occur over a couple of 100 kilometers, for example. So that's secondary circulation. And then even smaller than that is what we call tertiary circulation. Now, those are things that we experience and we can actually see from ground level, if I can put it that way. So tertiary circulation is on a very small scale. So something like a big convectional thunderstorm or a tornado, for example, it happens on a very small scale, over a couple of kilometers, and they don't last for more than like a couple of hours, maybe even a few minutes. So just be aware that we get these different levels of global air circulation. But the one that we were referring to now in this question, global air circulation, that large scale movement of air. Right, so let's fill that in. Right, large scale movement of air, global air circulation. Right, 1.3. The difference in air pressure causing air to move from an area of high pressure to an area of low pressure, what is it referred to? We have a look at that set of options once more. I've just been speaking about the idea of pressure gradient force, all right? So pressure gradient, remember, was the difference between the high pressure and low pressure. The force is what acts on the atmosphere, basically creating air movement, creating wind that moves from high to low pressure. So pressure gradient force is what they're looking for here. Right, 1.4. It says that winds blowing parallel to the isobar in the upper atmosphere are called what? Okay, now I'm going to need to explain this by drawing a diagram. So let's just extend our page a little bit here, if I can get that to do that. All right, there we go. Okay, So I've said to you that air will move from an area of high pressure, let's assume that's a high pressure, to areas of low pressure, okay? So air always moves towards the low pressure. Now we have a name for that, it's called the pressure gradient, so I'm just going to label it as pressure gradient or pressure gradient force even, okay? Now what happens in the atmosphere? We already know that Coriolis force also acts on the atmosphere, so it kind of pulls the air in a different direction, okay, because of the spinning action of the Earth. However, in the upper levels of the atmosphere, Coriolis force is equal and opposite to our pressure gradient force. Okay, so I want you to imagine that in the upper atmospheric levels, there's a giant tug of war going on. Okay, so air is being pulled towards the lower pressure because it's governed by that physical natural law. But at the same time, Coriolis force wants to pull it in another direction. So that's like this tug of war. And they're both pulling in opposite directions. Okay? So when they're pulling in equal, in other words, equal force or by the same strength in opposite directions, the air can't move anywhere but directly in between them. Okay? So when we're talking about geostrophic wind, okay, maybe I should put this in a different color so you can see it more clearly. Okay? It means that the air, due to the fact that it's pulled in equal and opposite directions, will move parallel to our isobar. So imagine that that's an isobar there and there. Here is our geostrophic wind. Right, it's been pulled parallel to these isobars because Coriolis force is in the same strength but opposite direction to pressure gradient force. Now, I just want to explain a little bit more about that as well, because you might be wondering, well, why is Coriolis force equal and opposite to pressure gradient force? Okay, in the upper atmosphere, about a couple of kilometers above the Earth's surface, there's very little uneven surface of land to slow the wind down. So we say there's very little friction, okay? So our wind speeds are extremely fast in the upper atmosphere. You've been learning a bit about jet streams, which travel from west to east at about 300 kilometers per hour. They travel that fast because there's no friction from the land surface slowing them down. Now, as the wind travels faster, in other words, as pressure gradient force is stronger, Coriolis force also gets stronger at the same time. So we've got this very fast wind pulling in one direction. Coriolis force also grows to very, very great strength, pulling it in the opposite direction, causing that air to move parallel to your isobars. Okay, it's quite a complicated sort of term that you need to know about, and you need to really have a look at past question papers with the diagrams as well, just to help you identify which part is the pressure gradient force, the Coriolis force, as well as your geostrophic wind. So to answer that question, okay, wind that blow parallel to the isobars, they are called geostrophic winds. And the best example that we have of those is our jet streams in the upper atmosphere. Question 1.5. If we have a look there, winds that blow in the tropics, okay, so within the tropics means between 0 to about 30 degrees north and south. What are they called? Let's have a look at that list of options once more and see if we can find it. Okay, you should know your global air circulation very well to do this. Our trade winds, our tropical easterlies, that's the correct option there. So you really need to know that diagram showing your global air circulation very well. So our trade winds in this context is the correct answer. However, they can also be called our tropical easterlies. Let's have a look quickly at our next question. All right, this is a nice easy one, and it refers back to your grade 10 syllabus. So we're looking at figure 2, showing igneous intrusions to answer the questions that follow. So let's just clarify what we mean by igneous intrusions to begin with. Last year, in grade 10, you learned that there were 3 rock classification categories. And now the first of those is called igneous rocks, which means that they are formed from magma and lava that solidify either below or above the Earth's surface. Now when hot molten rock cools down and crystallizes below the Earth's surface, we learned that's called igneous intrusions. It's inside the Earth's surface. And then when we have lava above the Earth's surface, which cools down and makes really small crystals, that's called extrusive igneous rocks. So this particular diagram is looking at igneous intrusions. Just remember your two other categories, sedimentary as well as metamorphic rocks. So let's just have a look at the diagram first, and we'll probably take a little bit of a break, and then we'll go back to those questions. So let me just have a look very quickly, and then I'll give you guys that break.
Awesome stuff. All right, then, guys, let us just take that break. I can see that some of you are asking questions right there on our Facebook page. Please do keep them coming so that after the break, we can try and answer as many as possible. We'll see you after this. Welcome back, grade 11. We are grade 11s. We are doing geography right now, and I'm sure that you guys are really learning more and learning extra. It is, of course, the exam school with me, Pumi, and Michelle.
Thank you very much, Pumi. All right, so the previous set of questions that we were looking at was to do with global air circulation and pressure gradient force. So if there are any things that you want to ask about that, because I know that there are tricky sections, please make sure that you're asking those questions so we can revisit those at the end as well. But before we went to the break, I was looking at intrusive igneous rock and the formations that they could possibly do, and I was going to go through that diagram quickly with you guys. So let's just have a look quickly at the diagram before we get to the questions. All of the shaded grey regions that you see on this particular diagram are showing igneous intrusions, more or less. So you'll notice that they have various different shapes. So number 3 here, okay, you'll notice it's a very large sort of shape. It extends very, very far, and it's very deep as well. And we have a name for that. That's called a batholith, okay? And batholiths are characterized by their great depth underground and also their very large crystals. So we generally find very valuable minerals at those depths as well. So that's called a batholith. If we have a look at a couple of other things as well, number 2 there, you'll see this particular feature next to it. It's cutting vertically through the rock, okay? We have a name for that as well. It's called a dike. It cuts across sedimentary rock layers. So all the sedimentary rock layers that you see are these layers, parallel layers over here as well. Then if we have a look at number 1, you'll notice it also has a distinctive shape. If you use your imagination, it looks a bit like a mushroom, okay? So when we see that mushroom-shaped intrusion, which spreads between the horizontal rock layers, and because of the amount of magma forcing its way through, also pushes the overlying layers upwards, that is called a laccolith. Okay, so you need to know these names. Then if we have a look at a couple of others as well, we have a look at number 5. It's just a horizontal intrusion there. It's spreading between rock layers. We call that a sill. If we have a look at number 7, okay, it looks a little bit like the opposite of a laccolith. Instead of its mushroom shape pushing upwards, the weight of the magma is actually causing it to slump downwards a little bit. It's making more of a basin shape. That is called a lopolith. Okay, you need to remember that as well. If we have a look at this volcanic area here, number 6, obviously it's leading towards a volcano, will cause lava to kind of spill out of that area. Well, that would be called a pipe, a volcanic pipe. And we actually have one of our very own in South Africa. The Kimberley Big Hole is the remains basically of a big volcanic pipe. And all the kimberlite in that area has left us with these, well, would or did in the past, leave us with all these diamonds that were obviously mined, creating that big hole in the Earth's surface after they had finished mining there. So if we have a look at the questions, we have to label a couple of things there. So 2.1, we have to name the largest, there's your clue, it's the largest igneous intrusion labeled 3. I said to you that's called a batholith. Notice the spelling, please, guys. You need to make sure that you can spell these correctly, because in the matric exam or any exam, if your marker can't read what you're trying to say, they're obviously not going to give you those marks. Then for question 2.2, we have to label igneous intrusions 1, 2, and 7. So let's just revisit that diagram just to make sure that we understood what they were. So number 1, there it is there, that's that mushroom-shaped rock. Number 2, it's cutting vertically across the layers, sometimes diagonally as well. And then number 7, that intrusion that kind of causes the layers to slump down because of the weight of all that magma. There's our lopolith there. So number 1 was our laccolith. Notice the spelling once more. Okay. Number 2 was a dike. And then number 7 was a lopolith. Right, you must know each of those features by name. 2.3. It says here which landform would develop if number 1 is exposed to at the Earth's surface. So let's just have a look there. Alright, so first thing we need to observe is what would cause it to be exposed at the Earth's surface. Now remember, the overlying layers at number 1, above this laccolith, they've been pushed upwards, making almost like a hill, okay? And sedimentary rock is less resistant to erosion, so water could get through there, wind could erode it, and so it will gradually over time erode all of those overlying layers. Now one thing about igneous rock is it's extremely hard and it's very resistant to erosion. So after all of that sedimentary rock that are colored in green there is eroded away, it will leave behind this dome-shaped feature from that laccolith, sometimes even from a batholith. And because we're talking about fairly deep igneous rock, we usually associate that deep intrusion with a granite, okay, which is a type of igneous rock. So they're looking for the word dome, okay, because it literally makes a dome shape. But more specifically, it forms a granite dome, okay. So you need to know that as well. So at number 1, if it's exposed, it's going to form a granite dome. But they will give you the marks just for the word dome as well. Alright, so again, I encourage you, any of these sections that you're not quite getting, you need to make sure you send those questions in so we can go through a couple of things again. Alright, let's have a look at question 3. It says, refer to figure 3 showing the West African monsoon winds and answer the questions that follow. And I've given you 2 diagrams to look at here. Now, before I get into those diagrams, there are basically 2 case studies that you look at when you learn monsoon winds. And remember that they are part of your regional air circulation because they occur over continents or subcontinents. They're not a global air circulation, although they consist of features of that global air circulation. So over West Africa is the one example that we'll look at monsoons, but also more commonly they occur over India, and that's why we get monsoon rains, for example, the wet and dry monsoon of the subcontinent of India. And it all goes back to knowing your global air circulation diagram. And knowing that diagram is not only for this particular syllabus, but you need to know elements of that for next year as well. So you must make sure that you're going through all of those elements, the pressure cells, the belts. You need to be going through your wind belts as well. Those play an integral role in all of the air circulation that we've been looking at up until now. So back to my question there, monsoons. Okay, monsoons, they basically refer to a seasonal reversal in winds. So in other words, your winds might be coming from the northeast one season, and then the direction of those winds completely changes in the next season. They might become southwesterly. And that's got a lot to do with our change in our seasons. So let's just have a look at this particular diagram. And the first thing I want you to notice is the position of this line here. Okay, you must know what this refers to. It is called the ITCZ. Okay, there it is there. And if we have a look over here, it's shifted in this particular diagram. There's your ITCZ. Okay, you need to know what that stands for. ITCZ stands for Intertropical Convergence Zone, and it's basically where all of our equatorial low pressures originate. Okay, so ITCZ, Intertropical Convergence Zone. Now it's a convergence zone. So that means that winds converge, they meet at that particular area and actually cause what we call a trough or a front, a moisture front in that region there. So we've got winds coming from the northeast, okay, in this area here, also over here. Those are known as trade winds as well. They're coming from the northeast. And then we also have southwesterly winds, which are converging at the ITCZ. Now, I also want you to remember that ITCZ, the convergence area, when air converges, it also rises at the Earth's surface. At the same time that it's meeting at that ITCZ, that air is also lifting, it's rising, it's creating thunder showers, it's creating clouds, lots of condensation, and obviously lots of rain. So wherever you see that particular line, you must know that that's pretty much where your thunderstorms are going to originate. That's where all your equatorial low pressures are. Okay. Right, now, a couple of other things. This is quite a complicated section. Right. When you learnt about air masses, you learnt that we have what we call continental tropical air masses. Okay. And because they originate over continents, they're quite dry. All right. Then we learnt about maritime tropical, or even sometimes called equatorial tropical air masses over the oceans. So this is our Atlantic Ocean here. And quite near the equator, you must also remember that the air is very hot, very moist, very humid because of all that heat that the equator retains, because it's heated very concentratedly via our insulation. So we got this hot air on this moist, hot ocean. So that air is going to rise. It's going to be absolutely perfect for condensation to occur. Now, when you have a look at these diagrams, notice that in this particular diagram, your ITCZ has moved northwards, okay? Now that's associated with the northern hemisphere summer, okay? When the ITCZ is over the Tropic of Cancer. Now because it's over this position here, we have very moist air driven by those southwesterly winds, which occurs over that West African continent or subcontinent, converging at this ITCZ with our northeast trade winds. Okay, so wherever you see these winds here, okay, maybe I should put them also in a different color here. Okay, these winds here, it's going to be moist, it's going to be humid, it's going to be hot. So they're going to get lots of rain in this particular region here. Okay? And that happens in the northern hemisphere summer. Remember, northern hemisphere summer, southern hemisphere winter. Okay, we are situated down here. We're getting colder temperatures because that ITCZ is very far north of us. Okay, so this particular green shaded region here, they will get a wet monsoon because of that southwesterly moist air coming off the maritime tropical area of the Atlantic Ocean. But then it gets reversed, okay? So in our summer, so we got the southern hemisphere summer here, northern hemisphere winter here, okay? Our ITCZ has migrated south towards the Tropic of Capricorn, okay? So now air is converging at a different place. So we've got this air coming in from the north here. It's coming from a continental area. So that means it's going to be very dry, but also very hot because we're in tropical areas, okay? So this region here, if I use another color here, will experience very dry and hot conditions, because that air is only converging now at this point here. So this entire area that I've marked off here is going to be very dry, very hot, and only these areas right in the western parts of the southern parts of West Africa here are going to experience rain from that moist tropical Atlantic air. So you really need to understand the ins and outs of this particular diagram, and you really need to know your wind belts and your ITCZ equatorial low pressure zones here. Let's have a look at these questions, or these couple of questions that are coming up here. Firstly, let's just go back here. Here we go. What is a monsoon wind? I explained to you that it's a seasonal reversal of wind. And that's because of our shifting ITCZ, our shifting pressure belts. Question 3.2, we have a quick look at this one here. Got a little bit of time. Identify the wind which dominates West Africa from January to March and then from June to September respectively. Okay, so if we have a look at that diagram once more, okay, notice the direction from which these winds are coming. So we've got northeasterly winds, okay, and then we've got southwesterly winds as well, okay, and they all interact with that ITCZ. Okay, so we've got our northeasterly winds. Okay, and we've got southwesterly winds as well. All right. If I just go back to that diagram, because you might be getting confused with the seasons here. Let's just put a little marker there. So this would be January. And this would be June. Okay, so don't get confused there. June being northern hemisphere summer, January being southern hemisphere summer. Okay, so these are basically our trade winds that are converging at the ITCZ. Okay, question 3.3. It asks you to describe the weather in West Africa as a result of the wind that blows from June to September. All right, so we're looking at our June diagram here, and we're focusing on this area that I shaded in over here. I said to you it's going to be very moist, very humid, because that moist, warm, tropical air is coming off the ocean towards the ITCZ. So we need a couple of characteristics there. So it's going to be very humid. Okay, it's going to be hot or warm even. Okay, it's going to be very conducive to rainfall as well. So our rainfall increases. All right. Let's quickly go to 3.4 and 3.5. One problem associated with the monsoon wind that blows from January to March. Now, January to March, it's our summer, northern hemisphere winter. Okay, so it's going to be dry and hot. Okay, so it's going to be very dusty, very uncomfortable actually. Very dry and very hot. It's going to be very dry, hot wind, and dusty as well, because all that dust from the Sahara Desert is taken along with it. And 3.5, one problem associated with the monsoon wind from June to September. Well, if it's bringing lots of rain, it could result in flooding. And also the humidity levels must be through the roof. It must be very hot, muggy, uncomfortable. But the main idea to remember there is flooding. I think you deserve a little bit of a break, and you'll carry on afterwards.
All right then, mindsetters, let us carry on after this very short break. Welcome back from the break, mindsetters. You are still watching the exam school, and we really are appreciating all of the questions that you are having for us. And yes, Michelle, we have a question from Gibbon Kachutelo asking, how does tropical cyclones and westerlies affect Western Cape's Mediterranean climate?
Okay, given this section actually more pertains to the grade 12 syllabus, and immediately there's a little problem that I need you to sort out. Okay, so tropical cyclones do not affect Western Cape. You're probably thinking of mid-latitude cyclones. Okay, it's on the west coast. Tropical cyclones don't affect the west coast of South Africa. They only affect the east coast, and they originate from the tropical easterlies in very warm waters. Okay, but the Mediterranean climate owes its existence to the fact that frontal and cyclonic rainfall is developed from a mid-latitude cyclone. Alright, so mid-latitude cyclones, and you learn about this next year, so don't stress if this sounds a little bit confusing. But mid-latitude cyclones develop at 60 degrees north and south. And they develop at a region called the polar front. And it's the westerly wind belt that drives them towards the east, and that's what causes them to affect the Western Cape. Right, so just please don't get confused between a tropical cyclone and a mid-latitude cyclone. While they are both low-pressure systems, they form under completely different circumstances, and they affect our weather in very, very different ways. All right, so given, I really hope that helps you. Are there any other questions, or could we move along, do you think?
Let's move right
All right, cool. All right. So, next question that I've got for you deals with the idea of El Niño southern oscillation. Now, El Niño is another section that I find that students, they battle to grasp immediately. And it's all about knowing what causes these conditions to occur and being able to interpret the diagrams nicely. So let's just have a look at these this particular diagram and see if we can make some sense of it. All right, so we've got figure 4 here, and we need to answer the questions relating to this diagram. Now, they've given you Australia, which is over here, and they've given you the west coast of South America over there. Now, they've told you here that warmer water is congregating towards the west coast of South America, and we have cooler water, which is a kind of pooling or welling up the coast of eastern Australia. Now, first thing I want you to get right in your minds is what warmer sea surface temperatures do to climate and what cooler sea surface temperatures do to climate. Air assumes the same characteristics of the water that it rests above. So if we've got warm surface water, then we're going to have warmer air above that water. It assumes the same temperature. Therefore, warmer air, because it's lighter and it's denser, it will rise, and that will create a low pressure. Now, you should know by now that low pressures and rising air are associated with large-scale evaporation. So water will get evaporated into the air, and it will condense at that dew point level to form clouds, which we get our rainfall from. Now, when we have colder water, obviously the reverse happens. So we've got cooler air above that cooler water, assuming those characteristics. Colder air is denser, it's heavier, so it sinks. And sinking air creates a high pressure. Sinking air cannot create evaporation and moisture uplift into the atmosphere. So we're not going to get rain where we have a high pressure system. So you need to understand the dynamics of low pressures and high pressures in order to understand El Niño as well as La Niña. Okay, so when we're dealing with El Niño, the other factor that comes into play here is the strength of our tropical easterly wind belt. I want you to imagine in your mind's eye that the areas experiencing El Niño and La Niña, it dominantly originates from the areas between about 5 to about 30 degrees north and south, or 0 to about 30 degrees north and south of the equator. So when we have trade winds, we don't have them blowing at the same strength every year and year in, year out. The intensity can vary from year to year. All right. So another thing that I want you to get right in your minds is that El Niño is associated with weak trade winds, all right, and La Niña is associated with strong trade winds. Now, they don't really fully understand why these winds, they have like an 18-year cycle, 9 years strong, 9 years weak. They don't really understand the dynamics perhaps behind that, but we know the effects that it will have on our climate across the globe, all around those latitudes. All right. So with El Niño, before we actually really get into the actual questions, let's put that back there. I want to just draw a little diagram with you guys so that you can understand the dynamics behind El Niño. Okay, let's just get a little bit more space here perhaps as well. Okay, so let's say, and this is going to be a very rudimentary way of drawing it, let's say that this particular block here, that's Australia. Okay, then we've got a whole ocean, right, and that's the Pacific Ocean. And then we've got the west coast of South America. Okay, so I'm just going to call that South America. All right, so along this latitude of about between 15 to 20 degrees south, let's say. So the first thing we need to look at is the strength of our trade winds. Okay, so in El Niño, okay, our trade winds, the arrow that I've just drawn there, trade winds are going to be weak. Okay, they're not going to be very strong. Okay. So if we have weak trade winds, okay, remember that winds also interact with the surface of our ocean, and they literally drag or pull water along in that same direction they're going, okay? So if we've got very weak trade winds, it means that our warm sea surface temperatures, our warmer water, warm sea surface temperatures, will be along the west coast of South America, okay? Now because we've got warm sea surface temperatures there, it means that air is warmer above it, it rises, creating a low pressure. Okay. As that air rises, it evaporates more moisture. It's going to create clouds, condensation, and rain. Okay. Show a bit of rain there. So that means during an El Nino event, the west coast of South America actually gets more rain than it's usually associated with. Okay. Now, if we've got warm water on the west coast of South America, it means that our cooler water gets a little bit displaced. Okay, so we've got cool water, cool SST, sea surface temperatures in other words. Okay, so that means that the air above that water is also going to be quite chilly, cold. So it's denser, it's heavier, it's going to sink, it's going to create a high pressure system. Okay, and high pressures, they can't evaporate moisture because there's no uplift of evaporated water, and so it's going to be very dry. Okay, so that means this area here, Australia, especially that east coast, will get very dry conditions, much drier than is usually expected for that area. Okay, so this is just one area that's affected by weaker trade winds, but you need to understand that this is also going on at all the other similar latitudes around the Earth. So that means Africa also gets affected by it, for example. Now when Australia gets drier than normal conditions, so too do South Africa. We actually go through dry, lower than normal rainfall amounts during El Nino years. So we'll have about 7 to about 9 drier years. Then it will go back into a La Niña phase. Now La Niña is the opposite of that. Okay, I don't really have too much time to go through all of that, but La Niña would be the exact opposite. There was trade winds would be strong. They would drag all that warmer water across to this area here, Australia, creating the low pressures in Australia rather than South America. So when we're dealing with a La Niña, it means the east coast of Australia will be getting wetter than normal conditions, and the west coast of South America will be getting drier than normal conditions. So like Australia, South Africa will also be getting wetter than normal conditions in a La Niña phase. Okay, so they kind of change, they shift, they set an oscillation, they change between a La Niña phase and an El Nino phase. Right, so let's go back to that diagram and see what the questions have in store for us. Okay, so question 1. Okay, so we've discussed the fact that if we have weaker trade winds, the warmer water kind of pulls towards the west coast of South America, and we'll have an upwelling of cooler water near Australia and Indonesia and those places there. So the name given to the circulation that's shown in this particular diagram, they're looking for the phrase El Nino, which actually translates to boy or Christ child. So La Niña, the opposite, a girl. All right, so the opposites in weather conditions. You don't need to know that, but you do need to know that they lead to the conditions illustrated above. 4.2, explain why there is more warm water on the west coast of South America. Now, as I've discussed with you before, move that up, that our trade winds in this case are going to be weaker. Okay, so they're not going to take that warmer water all the way across the ocean. It's going to stay in this region here. Okay, so you must be able to talk about the fact that there's weak trade winds. Okay, so weak tropical easterlies or weak trade winds. They cannot pull or drag water, surface water that is, towards Australia. So they don't have enough pull, they don't have enough drag, so all that water is congregating over Sorry, I think I put that in the wrong one, so I'll just put a little arrow there. Alright, it's not the end of the world. So I'll just put that over there. Okay, so they don't have enough pull to take all that water across the Australian Ocean there. Right, then, question 4.3, and I'll do that just above here. Explain why Australia will probably experience below average rainfall. Okay, so you need to realize the fact that they've got cooler sea surface temperatures. Okay, sea surface temperatures, there's my abbreviation there, which will lead to a high pressure, sinking air, and dry conditions, because there's no moisture being evaporated there because of that high pressure. High pressure is associated with sunny skies, dry conditions. Okay, question 4.4. What conditions is South Africa likely to experience during this time? So remember, I said we can be associated more or less with Australia. So we will have dry conditions or below average rainfall. Alright, so when you're answering these questions, they do like to throw in a couple of essays, and you're going to experience this quite a lot as well when you get to matric syllabus. So in a paragraph, okay, always please write it in a paragraph, otherwise they're going to give you 0, even if your answers are right. Describe some of the effects that the population on the east coast of Australia might face as a result of the reduced rainfall, and describe some of the strategies that could be implemented to reduce the severity of these effects. Okay, so it seems like a loaded question. You've got a couple of things to decipher there. So we already know that Australia's experiencing a high pressure and it's dry. So we need to have a look at how that affects their population and how that affects their economy, their food security, all those sorts of things. Then we also need to have a look at, okay, if they've got drier weather and they don't have enough food, or they reduced exports, or whatever the case may be, what can they do to alleviate those symptoms or alleviate that situation? All right, so when we have reduced rainfall, the first thing we're going to think about, well, we have water shortages. Okay, we're not going to have running tap water. We're going to have water restrictions even. Okay, we also are not going to be able to grow enough food, so we're going to have a lack of food security because our crops primarily rely on water, or water that has been stored in dams and reservoirs. So if we don't have crops, it means that we can't export that produce. It means that we might have famine because we can't feed the population. And it also means that we might have to import food, which is very, very expensive to do from overseas, because we have no exports, we've got no food, so we need to make another plan. And so the GDP of that country might also drop. So there's a couple of problems associated there, as we can plainly decipher. Then the strategies that we need to overcome some of these effects. We can't avoid the fact that there's going to be a drought, but we can make plans ahead of time. And one way to do that is to improve the weather forecasting. If we know that there's going to be a drought, we can store water, we can stockpile seeds, livestock feed, so that our animals don't experience famine. We can also impose water restrictions so that we save as much water as possible. Okay, and when commercial farms want to get a loan from the bank, for example, they actually employ meteorologists and climatologists to say what is the rainfall projected for this season, because they're not going to loan out money if they know that they're not going to get those returns, or they're going to be in debt because they've had reduced crop yields. So it's very important, even in the economic sector, that we know what's going to happen, more or less predict what's going to happen with our climate, and we use very, very complex climate models in order to do that. So there's quite a few things that we've spoken about there. Make sure that you choose at least one problem and then 3 sort of strategies to overcome various problems, or you can do the opposite, but you must answer each element of the question. Okay, you can't leave out anything, because then they won't allocate those marks. Right, so let's just paraphrase a couple of things there. So let's just have a look at the problems, for example. Okay, so very simply, we might have famine. We might get water shortages as well. Let's just put one more there at least, where we have space. We might have reduced crops, reduced exports, reduced GDP. Okay, and then when we're looking at a couple of strategies, let me just erase some of this because otherwise this is going to get in the way. Okay. Right, if we have a look at some of the strategies that we can use, one of the unfortunate things that we do is we impose water restrictions. All right. We can build reservoirs and dams. And all of these things store adequate water supplies. Okay. Education and awareness programs, we can stockpile seeds, stockpile livestock feed, awareness campaigns, water restrictions and laws governing our water use. All of those things are very useful to look at when we are trying to save water during a drought situation. And South Africa has done some of those things in the past. They have, especially I think it was in the 80s when we had such dry summers. They also imposed severe water restrictions. You couldn't water your garden at any time of the day you wanted. You couldn't fill up your pool or anything like that. It was very, very severe. And we needed to conserve some of those water supplies. Alright, so that deals with El Nino to some extent. Let's have a look at least one more question for the day. We're looking at figure 5, which is showing questas, okay, questa domes and basins to be more exact, and we need to answer the questions that follow. So, first thing I want you to understand is that questas come from a category of landforms that you have been studying, and they come from inclined landscapes, inclined layered sedimentary landscapes more often than not. And the first thing that you need to know is that inclined layers, so layers that tilt upwards, that's caused by tectonic forces, folding, warping, faulting. So that can cause the Earth's surface to warp or to fold or to tilt in various directions. Okay, so you need to know what the underlying cause is. Now, when we get folds forming, if you have a look at this diagram, okay, sometimes we get the land that's folded upwards, like you see there. That's actually called an anticline. You've done that last year as well when you looked at the process of folding. And then you'll see that these layers here, they dip a little bit down, okay? That's often called a syncline when you're looking at folds, okay? But for this particular question here, this is called a questa dome because the layers are literally folding upwards like a dome, okay? And then we're looking at a questa basin over here. Now, each of these features here, if you look very carefully, they're made up of kind of parallel ridges of rock, and those are your individual questas. In a questa, the folds are very gentle, so that means the ridges only incline at about 10 to about 25 degrees to the Earth's surface. Alright, so just remember that questas are the most gentle form of inclined ridges of sedimentary rocks. Alright, let's have a look here. 5.1, what is a questa? Let's quickly get as much as we can done. Alright, so it's a ridge of inclined strata. It's got a very gentle incline. About 10 to 25 degrees. Alright, then 5.2, the difference in the formation of the questas in diagram A and B. Now A, we saw that the layers are folding upwards. Okay, and B, the layers are going to fold downwards. I'm just going to explain the last question so that we can finish off today. When they ask you about a dip slope and a scarp slope, very quickly, okay, you'll see that there's a steep slope here, okay? That's called your scarp slope, and your dip slope is the gentle part over there. So the scarp slope, always look for the ridge that's very steep, gentle slope is always the dip slope. Now, unfortunately, that's all we have time for. I wish we could do more, but hopefully we'll see each other again soon. Hopefully it helped you in some way. Thank you, Pumi.
Thank you so much, Michelle. We really enjoyed the show with you today.
Thank you.
Awesome stuff. All right, then, mindsetters, we are very happy to have had you on our show today. Please make sure that you join us again next time right here on Mindset. It is, of course, the exam school that has been proudly sponsored by Macmillan and, of course, endorsed by the Department of Basic Education. But from you, Pumi, it is bye-bye.